My friends, what a journey we've been on. We have ventured through all of the deep net theory. We have the fundamentals of TensorFlow down now. We've built some relatively simple graphs in TensorFlow. We fit a model in TensorFlow. Now it's time to merge everything together and build some deep nets in TensorFlow. So we're going to visit our old intermediate net friend in MNIST, and we're going to convert it into TensorFlow. So I already have this notebook ready for you if you want to follow along. It's this intermediate net in TensorFlow, or you can build it alongside me freshly here. So give it a catchy name, intermediate net in TF, and we are going to give it a title, really the same thing. And then we're going to load our dependencies. Can give a heading that we're going to do that. Now, the general style here is from Aymeric Damian. He had a beautiful way of outlaying the graph for a relatively simple network, but we're not going to be building his multi-layer perceptron. We're going to be building the intermediate net that we built in Keras. So if you have a look back there was this Keras notebook that we built. So our network is going to look the same. You'll be able to compare back and forth when we're done to see exactly how close the architectures were. But you'll see how different TensorFlow is syntactically. So we're going to have our same old imports here, numpy, and setting the random seed. Same thing with TensorFlow. We're going to load our data. We're working back with our old friends MNIST digits. So this time we're importing them from TensorFlow. We hadn't done that before. So this is a little bit of a different looking import. Before we were importing them from Keras. Now the way that we're inputting them, we don't need to do any pre-processing like we did in Keras. So that's a nice little step. We need to specify where these MNIST data are going to go. So we can just put them in that directory there. And as we have largely done, we're going to one-hot encode our outputs. We've been doing that throughout these live lessons. I need to pluralize this, read data sets. Alrighty. So now we need to set our neural network hyperparameters. So previously when we were building our notebooks in Keras, we tended to put our hyperparameters down below, but in TensorFlow, our code starts to get really complicated, and so it becomes tricky to simply at a glance look into the notebook and figure out where everything is, what this number means, what that number means. So it's nice and tidy to put any of the hyperparameters that you can right at the top of the notebook like we're about to here. Set hyperparameters. So we are going to have a learning rate of 0.1, as we have found is really good. Let's have 10 epochs to start, and we're going to have a batch size of 128 MNIST images per batch for our stochastic gradient descent to work with. We're going to have, we have to explicitly decide how we're going to initialize our weights now. So in Keras, that was happening for us already using Xavier Glorot's suggestions. So this time, we're going to have to explicitly initialize that way. So here's some elements we're taking off the board. So we're going to be using gradient descent. We've decided on our learning rate. We've decided on the number of epochs that we're going to train over. We have decided on our mini batch size of 128. And we've decided on Glorot initialization. So in the next step, we're going to define the number of neurons for each layer. So if we look back at this notebook, I'm going to move it over here for convenience, we had 64 neurons in our first hidden layer, 64 neurons in our second hidden layer, and of course we have 10 outputs representing the 10 different classes of digits. So we're going to do the same thing here. We have the same number of inputs as we always have with the MNIST digits, 784 pixels. We're going to have 64 neurons in our first layer. We're going to have 64 of them in our second layer. And then we have 10 classes of digits to output. Now, we need to start defining elements of our TensorFlow graph. So first, we're going to define our placeholders for x and y. So let's do x, define placeholder tensors. So x is going to be a placeholder, and it's going to be single point precision digits. And it's going to be an array of length and input, which is 784. Again, as we did in an earlier notebook, we're arranging it in the second dimension so that the x is the right orientation for our matrix multiply with w when we actually execute this graph. So that's the kind of consideration that Keras was automatically handling for us, and now we need to think about explicitly. So in TensorFlow, we have to really be thinking about our operations at a matrix multiplication level, whereas in Keras, it was just happening automatically. So we're going to have the same float kind of situation here. And our output placeholder, it is going to represent the classes, of course, the 10 possible classes that we could have. And now, in this notebook, this might seem a little bit like overkill, but this is setting us up really nicely for the next notebook, because in this notebook, we're just going to have dense layers, but in the next one, we're also going to be adding in max pooling layers and convolutional layers. So we're just going to start things off right with a nice clean notebook here by defining our layers. So we're going to define a dense layer with ReLU activation. The dense layer is similar to this kind of structure. So it's going to take in an X, which is a tensor of input values, a placeholder tensor. It's going to take in a W matrix variable. It's going to take in a B bias variable. So that's how we're going to define it. It's going to take an X, W, and B. And within the neuron layer, we're going to calculate Z. So we'll do that just as we did a couple notebooks ago by adding and matrix multiplication. So we have matrix multiplication, matmul, of X and our weights matrix. And then we add to that our bias, B. Now, because we want to have ReLU activation, we're going to pass all of this Z into a ReLU activation function to give us our output A. So let's define that explicitly. A is equal to the ReLU operation on Z. And then this layer is going to return A. Great. And now we can design our architecture. So let's have a quick look back at how we did this before in Keras. In Keras, we had to specify the sequential model to indicate that all of our layers are going to fall in sequence. In TensorFlow, we're going to have to do that explicitly. So we're going to start off with our first layer. So we're going to define our network. As inputs into our network, we're going to have X, we're going to have weights, and we're going to have biases. So we start off with two dense hidden layers here. So 2 dense hidden layers. Some comments are nice because this could start to get messy. So our first dense layer is going to be defined by the function that we created up here. And that function takes in x. It takes in weights W1. We haven't defined that matrix yet. We'll do that next after we define our network. So our weights and biases, we're going to define those in a dictionary in the next cell. In the meantime, bear with me. So our second dense layer is also going to be leveraging our dense function that we created up here, and its inputs aren't going to be the raw inputs x. Its inputs are going to be the outputs of dense 1. So in Keras, where we were able to just say, oh, I want to create a sequential model and add on to that, here we need to be explicit and say my input into the second dense layer is going to be the output from the first dense layer. Similarly to just above, we're going to have weights and biases with a particular shape that we'll define next. And then we have a linear output layer that's softmax output layer. And this is going to be the Z of the output layer. So it's just going to be this portion of it. We're not going to do the softmax activation on it. That'll happen in a separate step. So just as we did in our dense layer here to calculate Z, we're going to take the result of matrix multiplication of our X and our W. And our X this time is going to be the output of dense layer 2. And the weights that we're multiplying against, we are going to define in the next step. And then we're going to add the results of that matrix multiplication to be two biases. And we're going to define that shape coming up next as well. And then this whole network function that we've defined here is going to return out layer Z. All right. So as I have now alluded to a number of times, we need to define dictionaries so we have these variable dictionaries. So these are going to be like these pink weights and bias variables. So we want those stateful variables to remain over multiple executions of the graph over all of our batches within the epoch, and then over epoch and over epoch. So to do that properly, we're first going to create a dictionary for our biases. The biases are a little bit simpler to define relative to the weights. So we use curly braces to define our dictionary in Python. And so first let's define bias B1 here for the first dense layer. And so B1, we're going to start it off as just zeros. So we're going to say our initialization is going to be zeros, and we have to define the shape that it's going to have. So it's going to be an array, a single dimensional array that has 64 neurons. We decided that above up here. And then for B2, it's going to be the same really. Let's just copy and paste it. So B2 is going to be the same as B1. It also, we just need to make sure that we change this over to a 2. So in case we change this later on, they're both 64 now, but we could decide to change those hyperparameters. And then our number of neurons with biases in the output layer, it's the same kind of thing here. We're just going to initialize with zeros. and the number of neurons in the output layer is equivalent to the number of classes, as it always has been through these notebooks. Now, we haven't talked about bias initialization on its own. We've talked a lot about weight initialization, and we talked about how we want to be using the Glorot initialization there. Now, because we're being so careful with the initialization of our weights, it means that we don't have to be so careful with the initialization of our biases. There's randomness being inserted into this equation initially by the W's, and so the B's, we don't need to think about it too much. We don't want to have super informative B's, so those we can set just to 0, as we've done here. Now the biases are behind us, so let's define our weight dictionary. So same kind of thing, we define it with curly braces, separating each element in the dictionary with commas, as we did with the biases. So our first weight dictionary is named W1. We use it over here in our network. And W1, we're going to initialize it, we're going to use the getVariable function that we used in an earlier notebook. And recall that when we use it, the first parameter is simply naming the variable. The second parameter, we have to define this two-dimensional weight matrix. And this two-dimensional weight matrix will need to be able to multiply it properly by x. And so it needs to have the right shape to be multiplied with our x, as well as with however many inputs we're going to have. So the rows on it correspond to the number of inputs, which is 784. And then the columns of this weight matrix is equal to the number of layers, the number of neurons rather, in our first dense layer. And we're going to choose to initialize with the weight initializer that we selected up here. So Xavier initialization is what we decided to work with, because it's been sensible in the examples that we've run through in the past. Now, W2 matrix is going to be almost the same. So, of course, we need to rename it to W2. Now, the number of rows in W2 needs to correspond to the number of columns in W1 in order to be able to complete this matrix multiplication in the network. So we can copy this value, and paste it in here. And then the number of columns in this weight matrix needs to correspond to however many neurons we're going to have in the second layer. So we can change this from a 1 to a 2, because the second layer is the dense layer. And then finally, we can output our weight matrix for the output. We'll do that in the same way with getVariable. And first parameter is just its name. The second parameter, just as above. So the same way that ndense1 was the output from weight matrix 1, it's the input to weight matrix 2. We do the same kind of thing here. So the number of columns in weight matrix 2 corresponds to the number of rows in the output weight matrix. And then the very final parameter is that the number of columns corresponds to the number of classes that we have, and that enables us to multiply the W out matrix by the number of classes that we have here without layer Z. So brilliant, here we go. And again, we're going to initialize in the same way with the weight initializer. There we go. And having done all that, we need to actually explicitly create an instance of a network now. So we're going to have we're going to build our model. So the output of our network will be some predicted values, some predictions, and then we'll call our network function here. We're going to feed in x weights and biases. So let's do that. X and then our weights are equal to our weight dictionary here. And our biases are equal to our bias dictionary. That's it. That one's easy. And now we need to define our cost. So we're going to choose cross entropy cost. And we're going to calculate the cross entropy on the softmax transformation, activation of output layer Z. So the output layer Z is being output from our network into this predictions variable when we actually run our graph. And so we can define loss and optimizer relative to that. So our cost is going to be, this is a shorthand here for our cross entropy and reducing it from an array value into a single scalar mean. This function, this cross entropy function, takes two values. It takes our predictions and it takes the true labels y. So we haven't dealt with y in a while, but we defined the placeholder for y up here, which we'll fill in our graph later. So those are the true labels y, and these predictions are our model's predictions of what y should be, and then the cross entropy is defining our wrongness between the model's predicted y and the true y. We're going to optimize on that wrongness and try to reduce it. To do that, we're going to use our gradient descent optimizer, as we have been doing throughout these live lessons. And we're going to use a learning rate of LR, which we defined above, all the way up here. And we're going to minimize the cost function that we defined on the line above right there with our gradient descent. We are almost there. We're almost to building our graph. So we also want to evaluate our model. So we need to define our evaluation metrics. And to do that, we have a couple of steps. So first we want to identify when our best prediction, so the class that the model was saying this is most likely a 2, whenever that lined up with the label 2, we want to say, yes, that was correct. So to identify correct predictions, we're going to write this little line here. I'll explain it once I've typed it out. So we have two argmax functions here, and what that is doing is it's saying identify the highest prediction value and set that to 1, and then see where the ones are equal. So wherever we have a match between our model's highest class prediction and the true prediction, that will be identified by this little call here, by this line. And then, having that, we can calculate our correct prediction by this line of code. So we are simply converting we're creating a percentage from these correct predictions. We're saying what percentage of them did I get correct. This first term, this first part of the line creates a proportion, and then I multiply it by 100 to create an accuracy percent. As always, we need to have an initialization op defined. Something that we've been doing with all of our TensorFlow notebooks. And finally, we're at a stage where we can train our network. So we're going to train the network within a session. So recall that to do that, as with all of our TensorFlow notebooks, create an instance of the session here, and then we initialize all the variables in that session by running the initializer op that we defined just above. Now we're going to want to print some helpful things out to screen. So in Keras, we had nice helpful things printed out to screen automatically. Here in TensorFlow, we're going to have to build it explicitly. So when training starts, we're going to say that we're training for however many epochs we decided on. I think it was 10. So this will print out a nice reminder of what we selected. And then we're going to create a loop over our epochs. So for epoch, in however many epochs we have, in range epochs, we are going to start off each epoch with an average cost of 0, where you want to monitor this over the course of the epoch and be able to output it at the end of the epoch. And not just our cost, but we want to also have our accuracy percent, because that's what we got used to in Keras, was having our training cost and our training accuracy output. And then we're going to loop over all of our batches within a given epoch. So first, how many batches are we going to have? We need to calculate that. So we do that with this line. It's pretty simple. It's just the however many examples we have in our training set divided by our batch size of 128, converted into an integer for the number of batches. And then so we can say for I in the range of our number of batches, we have a loop. So first we need to create our batch X and our batch Y for this particular step. So batch X and batch Y. There's a nice, helpful method here that we can call called next batch, and it just does the work for us on the MNIST data on the training set, so that's nice and easy. And then we need to feed these batch data to run a single step of stochastic gradient descent optimization on this single mini batch. And so to do that, we're going to feed and fetch data. So we're going to feed in our batch X, our batch inputs, and our batch Y, our outputs, and then we're going to fetch the key information, which is the cost and the accuracy. So let's write a line of code to do that. So we do that in the session run as we have been doing. So for all of the information that we are going to be fetching, we want to fetch the optimizer, our cost, and our accuracy percent. And then we need to feed in a dictionary of our batch X and our batch Y, as we have been doing in our examples of TensorFlow earlier. So this is good, we're getting there. And then we want to use the batch cost and the batch accuracy to calculate, to accumulate a sense of our average cost or our average accuracy percent over all of the batches within a given epoch. So we do that by simply adding them in. accuracy divided by the number of batches. Great. So that's pretty easy. So over each batch, we simply add on the batch cost, and we can divide that right away by the number of batches because we know exactly how many batches there are going to be. And that's it. That's how we train, step by step. So we want to have some helpful items that we're printing out. This is a little bit long to write, so I'm going to just pull it out of the completed notebook and explain it. So we have that in here. So we want to print out logs of our progress to screen. So after each epoch, and this will become clear, that is run, we want to make it clear to the screen that epoch has started or has run, and then we want to get the average cost across that epoch output to screen and the average accuracy output to screen. So that enables us to ensure that everything's running fine, just as we did in Keras, where it happened automatically. And then after all of the epochs have run, in our case 10, it will say training is complete. We're now testing the model. And to test the model, so we'll create a test cost. We need to feed in not the MNIST training data as we did into training, but the test data. And same thing for the Y. And we're going to do the same kind of thing for accuracy. So we'll just copy and paste the line, test accuracy %. And then we're going to do that, we evaluate the accuracy percentage operation that we created up there. And exactly the same, we feed in our test images and our test labels. And finally, we want to print something helpful to screen. This again would take quite a while to type this out, so I'm just going to copy and paste it. So we're going to print at the end of everything our test cost and our test accuracy with this particular formatting. So let's see how this looks. So training for 10 epochs came out as we defined it up here, and then we have our cost and our accuracy being output after each training session as we asked it to here in this format. And then we reached this training complete testing model, and our training cost got lower, and our test cost wasn't too high either. Our training accuracy got higher, and our test accuracy was pretty good, 96.97% after just 10 epochs of training. So it seems like we did this right. I'm feeling pretty confident that we succeeded through all of these steps, all of this matrix algebra that we had to complete, all of this initialization. We've succeeded in building a pretty good quality neural network here. Now, this neural network isn't too sophisticated. It only has 2 hidden layers. So what would happen if we brought together all of the information that we've learned here? We throw in some convolutional layers, some max pooling layers, and we build the Linnet 5 that we created earlier in Keras into TensorFlow as well.